Okay, so let's look at another example for curve sketching. So the first one we looked at was a polynomial. Those are pretty basic. It's hard to kind of do anything screwy with those. Um, but this one is a rational function. You got to be a little bit more careful. Not to mention the derivative is slightly more tedious. I mean, it's not super difficult, but it is a little bit more tedious than just doing a regular polynomial or a polynomial. This is not a polynomial. But we're going to do the same process. So we're going to take the first derivative. So we have the quotient rule. So we're going to do the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. And then we'll just simplify the numerator. We're going to set it equal to 0. And one thing that you do need to pay attention to is the domain of these rational functions. So where is the denominator going to be equal to 0? In this case, it's not ever going to be equal to 0. So we don't really have to worry about that in this particular case, but you do always need to check that. And really in any case, but polynomials, obviously the domain is all real numbers. Exponentials, generally speaking, is all real numbers, at least the ones we're probably looking at. So that is one thing to consider. In this case, the domain is still all real numbers, so it doesn't really come into play. So let's simplify this numerator. We'll go ahead and cross multiply with the bottom. And so when we set this equal to 0, as long as the numerator is equal to 0 and the bottom is not equal to 0, which it never is, the numerator is all we're concerned about. So I'll just write that and worry about well, I will write it here because we need it for the second derivative, but generally speaking, to get the critical values, we don't. Whoops, that is x cubed. Plus 18x minus 2x cubed all over x squared plus 9 squared. And then we have 18x over x squared plus 9. And like I said, so there's our first derivative simplified. And then, like I said, set this equal to 0. We're really only concerned with where is the numerator equal to 0. So we have x equals 0. And then we'll put this on a number line. And so you can plug in a negative number. You can plug in a positive number. And when you do, you see that first derivative is negative when x is negative. It is positive when x is positive. All right, now we're going to do the second derivative. So y double prime, and we're going to do that one there. So we have the bottom, x squared plus 9 squared times the derivative of the top, and then minus the top times the derivative of the bottom. So we're going to bring the exponent down. So we have a 2 times the x squared plus 9, subtract 1 from the exponent, so that's just 1 now, and then times the derivative of what is in there, so times 2x. And then that is all over the bottom squared, so now it is x squared plus 9 to the 4th. Simplify the numerator. So what we're going to do is we have x squared plus 9 squared. In that term, we have x squared plus 9. In this term, we're going to factor out, I guess we can factor out an 18 as well. We have 18 in both. So let's factor out 18 times x squared plus 9 and see what we're left with. So now we have x squared plus 9 is the only thing left in that one. Minus, we have x times 2. That's factored out. The 18 is factored out. So we just have 2x times 2x, which is 4x squared. And all of that is over x squared plus 9 to the 4th. This will cancel out with one of these. And then we have 18, and we don't need to distribute the 18. this will be times negative 3x squared plus 9 all over x squared plus 9 cubed. And so we set that equal to 0. Again, we're just worried about the numerator. It's a 3. We're just worried about the numerator. So 0 equals negative 3x squared plus 9. And we will see that we can bring the 3x squared over, divide by 3x squared equals 3. So x is plus, I don't know why I keep doing that, plus or minus square root 3. All right, needs to stop. Okay, I think I see the issue here, maybe. Okay. All right, so then put this on a number line again. Negative square root 3 and positive square root 3. We can use our polynomial trick here again, like we did in the first video and like we've done in other videos where we talked about this kind of thing. The denominator is always positive. So the sign of the second derivative is completely determined by the numerator. And in particular by this quadratic. Now this is a quadratic, it has a negative coefficient in front, so it's going to be the upside down parabola. So the second derivative is going to be negative, positive, negative. All right, now following the same pattern that we saw in the first video with polynomial, let's find the limits. And this is especially important with rational functions. You do definitely need to do this with a rational function. And so like we talked about in the last section, when we take the limit, we can divide by the highest exponent term in this. So when we do that, I won't write it out because we don't have enough room. But we'll have 1, divide everything by x squared is what we're doing. 1 over 1 plus 9 over x squared. And then when you plug in infinity, the 9 over x squared goes away and we just have 1 over 1. So the limit as x goes to infinity is 1. And doing the same thing, we will see that the limit as x goes to negative infinity is also 1. So we have horizontal asymptotes at y equals 1, no matter which direction we go. And then the x-intercept, so we're going to set the function equal to 0. And again, the numerator is the only thing that matters when we're equal to 0. And so we get x equals 0. Y-intercept, we'll plug in 0 for x. And f of 0 is 0. So the origin is the intercept. That is the only one. All right, so we got all the parts that we need. And then the last thing we need is to put the critical values from the first derivative and the second derivative together on a table and see what the shape of the graph looks like. So we have negative square root 3, 0, and square root 3. And then we're going to do the same thing where we look at the first derivative and the second derivative and see what the shape is. So we have y prime, y double prime, and the shape. All right, so y prime is negative when x is negative, positive when x is positive. So negative, negative, positive, positive. And then the second derivative is negative on the ends before and after, before negative square root 3 and after positive square root 3. And then it's going to be positive in the middle. I guess the other thing we need to make sure of, which we kind of talked about this, the domain's all real numbers, so there is no vertical asymptote. That's another thing to make sure that you pay attention to with these rational functions. But in this case, we have no vertical asymptote. All right, so decreasing concave down looks like that. Decreasing concave up looks like that. Increasing concave up looks like that. and then increasing concave down looks like that. All right, and then we could get the values at these points. So we plug in negative square root 3, and we get 1/4. We plug in 0, we get 0. We plug in square root 3, we get 1/4. I would say that's not too important on this one because we're pretty limited in where we're going to go. So let's draw our axes, and you can plug those in, but we're only going to put negative square root 3, positive square root 3. We have 0 here. And then we're just going to basically plot these ordered pairs. So we'll put it up here, and there's the origin, and then square root 3, 1/4. All right, and then the only other thing you got to make sure is we have a horizontal asymptote at 1. So let's draw our boundary here for the asymptote. And so we're not going to go above that because we're always decreasing from negative infinity to 0. So we are decreasing and concave down to there. We are decreasing concave up to there, increasing and concave up. So we're just following along here, increasing concave up, and then increasing concave down, and we're going to approach that asymptote just like that. All right, and there is that one. So not too big of a deal. You do need to make sure you pay attention to the domain, find the asymptotes, and then the rest of it is just like the polynomial.